So our first presenter will be Simon Grevenhorst from Karlsruhe Institute of Technology in Germany, and his presentation will be about the distribution grid monitoring based on widely available smart plugs. Floor is yours.
Yeah, thank you for the introduction. My name is Simon, and I'm from Germany, from Karlsruhe. I'll now talk a little bit about the distribution grid monitoring using smart plugs. And first, a little bit about the background. So as you all know, the distribution grid is changing, and there's a lot more renewable generation being introduced, and also a lot of new loads, for example, heat pumps and EV chargers. And both of these types of new technologies and appliances that are being introduced lead to voltage level fluctuations, and there's a permissible voltage band that is okay between 0.9 per unit and 1.1 per unit in Germany. And so there's, for example, demand side management as a technology to keep this voltage level in this range. However, we need to know the voltage level, of course, in the distribution grid to do all these kind of things and to do demand side management, maybe to use other flexibilities in the grid. But the instrumentation is missing, basically. So we talked a lot with our local distribution system operator, and in our city, like the substations are instrumented about 30% of the time. And so they have only a very broad overview of the whole grid, and therefore the grid monitoring is very hard. And other authors tried to combat this, and for example, there was a voltage measurement device designed, purposely designed to do a demand side management. So basically they measure the voltage levels, and in case the voltage levels are too low, some connected appliance is shut off. So that's a very basic demand side management. Other authors developed smart plugs themselves to monitor voltage levels at a distributed kind of scale at multiple points in the grid, and transmitted the data via Bluetooth to a smartphone, and then from the smartphone to some web server or something. And another possibility, of course, to monitor the voltage levels in the grid would be smart meter data. However, in Germany, at least, the smart meter rollout is going very slow, and also I think in other countries, I think the Nordic countries actually are quite far with smart meters. But those technologies also have some drawbacks. For example, most of them only record data every 15 minutes or sometimes every hour. And for live demand side management, this is sometimes too slow. And so a possible solution would be to use smart home hardware. In this case, we looked at smart plugs. So we compared some wireless technologies and decided that Wi-Fi would be a good option, like compared to Zigbee, where you need some Zigbee gateway to connect to some server, or LoRaWAN would be another possibility, but this bandwidth is very slow and you also need a gateway. And so with Wi-Fi connectivity, we can enable distributed measurements, because almost everyone has some Wi-Fi access point at home. And we also can do quite high frequency measurements. For example, in this case, about 1 Hertz. And these smart plugs, of course, are very low cost. So you can get them for under $10 or under 10 euros. But there are some questions, like what about the measurement error? Is this error okay for grid monitoring? What about the latency between the smart plug and our server? And what about an incentive for residents to install those measurement devices? So first, a little bit about our implementation. So as I told you, we use wireless smart plugs that connect just to an access point, send MQTT packets to a gateway or to our broker in the backbone, basically. And there we have a microservice kind of subscriber that is an adapter between the MQTT data, and our influx database. Furthermore, we conducted some modifications to the firmware. So we used the Tasmota open source firmware for our smart plugs and modified it a little bit to increase the measurement frequency from about 0.1 hertz, which is available out of the box, to about 1 hertz. And this had the this led to us disabling the current measurements, so the smart plugs can no longer be used for current measurements or power measurements, therefore, but we're only interested in the voltage monitoring. Then we also increased the measurement accuracy because there were some rounding errors in the firmware. We also did a pull request on GitHub, and we encrypted all the MQTT messages for a more productive scenario. And for the evaluation of the measurement error, on the right side here you see the standard, like the normal distribution of the error, and the blue, the blue rectangles, the squares, is our modified firmware with a standard deviation of about 0.27 volts. And the triangles in orange are the original Tasmota firmware with 0.33 volts. And for our test period of multiple weeks, we had basically no packet loss and very reliable measurement data. Then we also conducted a small case study with the EI.A 37 bus system. That is basically a representation of the distribution grid. And we included realistic line lengths and loads at all the different nodes in this grid, and did a Panda-Power power flow calculation to determine all the voltages at every single node and the line loadings. And then we simulated with our normally distributed error the monitoring of the grid using different number of smart plugs. And so another prerequisite for this case study would be that the distribution system operator knows the total amount of load that is in this grid area. So he has some understanding of his feeder level, basically. This is the graph how it then looked. This is the EI.A 37 bus system with a different amount of monitoring devices. And so as you can see on the left side in this graph, when just using few smart plugs, for example, 1 or 2, like the measurement error or the monitoring error in the whole grid is quite high at about 3 volts. And the more measurement devices are included in this grid area, the lower the monitoring error on average gets. And so on the right side, you can see this monitoring error for each node specifically. As you can see at the feeder level, these nodes are like almost white, which means almost no monitoring error. And far away from this feeder, the monitoring error gets a bit higher. So in this case, you could include more monitoring devices further away from the feeder and increase this accuracy there even more. So for the conclusion, we developed this new Tasmota firmware for our smart plugs and implemented them in our simulated scenario. We have a standard deviation of our voltage measurements of about 0.27 volts. Other authors found a monitoring error of 1.38 volts with smart meters, like the standard deviation, and 0.69 volts using AMI. We also have a very fast monitoring solution with a measurement frequency of about 1 hertz. And those devices are very cheap, so they can be deployed at a large scale. However, there are also some drawbacks to this monitoring solution. For example, when deploying smart smart plugs at the household level, other household appliances might lead to a local voltage drop. Then the line loads would lead just to a voltage drop due to the resistances of the local lines. And also an incentive for the residents would be needed to have those smart plugs in a lot of households in the grid. So we thought about different strategies for deployment. For example, we could allow the users, the residents of those smart plugs to control the loads that are connected, and maybe just use them as normal smart plugs as you could buy them, and then give them out basically for free in exchange for the measurement data coming from the residents. And the residents would also need to provide us with their internet access, of course. So this concludes my work and a little information about myself and some sources. Thank you.
So I think we have time for a couple of questions. Anyone?
Thank you for a nice presentation. I was wondering, when you go to deployment, I mean, this is very practical, but how stable are your, these smart plugs? I mean, to keep the connectivity, because if you first start to, put out, 20 smart plugs in a household, and you do that in the neighbor, and the neighbor, and the neighbor, and suddenly you have hundreds, you have thousands of smart plugs. And if they don't stay connected, you need really, for it to scale. I mean, we have tried with other sensors we have instrumented in buildings, and it's relatively stable, but wireless is not so stable as if it was wired.
Yeah, so we had our campus infrastructure to test, and so this, like the instrumentation or the connectivity at our campus is of course very good, and therefore we had no problems with connectivity. But I think another solution in a more productive scenario would be to just deploy more smart plugs, because they are so cheap and so easy to deploy as well. And also our backbone infrastructure with an MQTT broker is scalable, and so we could just deploy, maybe also deploy more brokers and more services in case that would be needed. Yeah.
More question? Yes.
How many devices were installed at your campus, and does this produce a large amount of sensor data? So is this in general also scalable for like thousands of households in a city, or do you think that like the MQTT broker could become a bottleneck there?
So right now we have deployed about 20 devices, and also from different manufacturers and using different hardware. But like we had no performance problems with the broker, and I don't know. I mean, you can look at MQTT brokers, I think, with multiple millions of clients or something, but yeah.
Maybe as a follow-up question, what are you using as the technology stack after MQTT?
So we have this microservice that's a MQTT subscriber written in Go, and that's connected basically to an influx database and just doing REST API stuff.
Okay, yeah, because I recently used Telegraph for that, but yeah, okay, you've got your own solution. Cool.
Thank you. Last question.
So you outruled LoRaWAN, and that because of the bandwidth? Because do you need I think LoRaWAN, you can easily have a city more or less on LoRaWAN, and so there are a lot of pros and cons, but maybe I can look it up in your paper. But by the way, thanks for a very, very interesting presentation. I definitely need to look into your weekend paper.
Yeah. So with LoRaWAN, to be honest, we thought at first that the transmission of the data would be maybe too slow or something. And also it was very easy for us to deploy them with Wi-Fi. And so the high bandwidth and not needing some gateway, and yeah, that was our reasoning for that.
Okay, thank you.
Thank you, Simon.